Section 1.3, Radical and Rational Exponents, Part 2 video. We're going to be rationalizing the denominator. That means anytime you have a radical in the denominator, you have to do a process called rationalization, which means you have to do something to the denominator to get the radical out. And in this instance, we have square root of 13. In order to get that radical to go away, I'll multiply top and bottom by the square root of 13. And what that gives me is this. It gives me the square root of 169 up on the bottom, and then negative 65 square root of 13 on top. And square root of 69 simplifies down to 13, and then you have square root of 13 up top. A couple of things you got to consider. Can I simplify that fraction? And you can. That would simplify down to negative 5, and then I've got square root of 13. Now I need to consider, can I simplify that particular radical? Well, it's a square root, so I'm looking for a perfect square to be one of its factors. So I'm checking 4, 9, 16. 16 is above 13, so I'm done. I cannot find a factor that will go into perfect square factor that will go into 13. All right, so by multiplying it by 13, I created a perfect square right there, 169, and that allowed me to get the radical out of the denominator. That's what's called rationalizing the denominator. All right, so another property that you can use is if you have a fraction underneath the square root, you can split it, okay? And then you notice, okay, I've got a radical in the denominator. Excuse me, you have to rationalize the denominator. This is a square root of 7, so I'm looking for a perfect square, which makes things a little bit easier because I'm just going to multiply top and bottom by the square root of 7. That's going to give me the square root of 49 on the bottom and then square root of 70 on top. And that's going to leave me with the square root of 70 over 7. Now, looking at this, can I simplify the square root of 70? Will 4 go into it? No. 9, 16, 25, 36, 49. I can stop right there because I'm over half of what 70 is, okay? Half of 70 is 35. So if I go over half that number and I haven't found a factor, then I'm good. This is your final answer right here. So that is square root of 70 over 7. All right. Now, simplifying radical square roots that have variables. So what I tend to do is I tend to split them. I tend to take care of my number, and then I tend to take care of my variable. All right. Now, with this, it just goes down to 5. Okay, because 25 happens to be a perfect square. But I'm going to rewrite the square root of G5 M8. So I'm going to write, I've got 5 G's. I have 8 M's. Now, my index, which is my root, is a 2. Okay, it's imaginary, but there's a 2 there, hence square root. Now, what I'm looking for is groupings of 2. So there's a grouping of 2, there's a grouping of 2. So I can pull out 2 G's, and I'm going to leave 1 behind. Now let's look at my M's. I got a grouping of 2 there, grouping of 2 there, grouping of 2 there, and grouping of 2 there. I've got 4 groupings. So I can bring 4 groupings out, and I have nothing left behind. So this is my answer. Now I expanded my variables. You can also say, okay, how many times will 2 go into 5? Well, 2 will go into 5 twice with 1 left over, right? And then you could ask yourself, how many times will 2 go into 8? Well, it'll go into 8 4 times. That's why I was able to pull out 4 groupings of M's. Okay, so you can also do it that way. But either way, you have to simplify it. Now, let's simplify this. We're looking at the fourth root. So again, I encourage you to make a flashcards or some index cards, really not flashcard, index cards that says 2 to the fourth, 3 to the fourth, 4 to the fourth, 5 to the fourth, and 6 to the fourth. Just write those down, get that on there. So 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256, 5 to the fourth is 625, and of course 6 to the fourth is, I think, 1296. All right, so we've got to have one of these numbers over here, one of these perfect fourth powers, be a factor of 1024. So you should see that 1024 happens to be the number that we're looking to see things go into. So we should see that that is the fourth square root of 256, and then it will also go into it 4 times. Okay, and then again we can also split our x to the 15, and we have that 7 sitting right there as well. So here we are, we have everything split, right? All right, so the fourth root of 256, well, that's just 4. So I got 7 times 4. Now I can't simplify the fourth root of 4 because the lowest number that I've got is 16, and 4 is below 16. So I'm just going to keep that, fourth root of 4. And then how many groupings of 4 can I have out of 15? Well, I can have 3 groupings of 4 because that'd give me 12, with 3 of them left over, 13, 14, and 15, right? So that would give me 28, once I clean this up, x cubed times the fourth root of 4x cubed. All right, so not really much different than what we've been doing previous. It's just a little bit, it's dealing with fourth roots, okay? Now, again, make sure you have that written down and keep it on an index card. Your perfect squares, perfect cubes, perfect fourth powers, right? Now let's look at this one. We are looking at, and I'm just going to go ahead and split it, the fourth root of 16 d to the 28 over the fourth root of 81 b to the 36. All right, so you should see right off, if you look at your perfect fourth powers, you should see that these are perfect fourth powers. Okay, so that's going to simplify down to, let's see, that is 2 over 3. Now, how many times will 4 go into 28? It'll go 7 times. So I have 7 groupings of 4. If I were to expand D out 28 times and put them in groups of 4, I'll have 7 groupings of those. Now, I can look at this one. How many groupings of 4 can I get out of 36? Well, if I were to expand this out, right, 36 B's, I can make 9 groupings of B's. Okay, so when you get done, this is 2d7th over 3b9th, and because our variable's not the same, so we don't have to worry about a quotient rule, and we're done. Now, let's look at this one. We're going to rationalize that denominator, okay? And what we're going to end up doing is we're just going to, again, split it. So we're going to say, okay, square root of 7 over the square root of x cubed, okay? So what would I need to do to get this to be a power of 2, multiples of 2? I got 3 x's, so that's 1 more than 2, but 1 less than 4. But so if I added another, if I said, okay, I'm going to do that, that's going to give me the square root of x to the 4th, which is just going to be the square root of x to the 4th. Well, 2 will go into 4 2 times. and that leaves me 7 square root of x up top. And I can't simplify square root of x, and I can't simplify 7, so I'll just bring this over, and that's my answer. But the key to this is saying, okay, I've got x cubed. I need to make it to be a multiple of 2's because I don't have any numbers. They're just variables. So the groupings will go in terms of multiples, right? And it's an index of 2 or root of 2. So I have to have it in perfect 2's in order. So I multiply it by x to the first to get it to be x to the fourth. Okay, and again, how many times does 2 go into 4, right? It goes twice, so that's why that's x squared. All right, one more, and we'll be done with part 2's video. Okay, now, so again, we're going to turn around, we're going to split this 27x cubed over 5y. Now, here, this is a really good example because we're going to have to multiply this by, we got to get a perfect square as a number, and we have to get the variable to be multiples of 2 because we're dealing with square roots. Okay, so I would need to multiply this by 5y. That would give me the square root of 25y squared. Okay, and that would give me 5y. 25 is a perfect square, gives me square root of 25 is 5. There's an invisible 2 right here. 2 goes into 2 one time. So that brought everything out of the denominator. So when I multiply 5y on the bottom, I have to multiply 5y up top. And that gives me the, let's see, that would give me the square root of 135 x cubed y. And you can simplify square root of 135. So square root of, I don't want that, of 135, not 185, 135. Well, I can split that down into, let's see, I could split that into, will 4 go? No. 9 will go, and it'll go 15 times. So that gives me 3 squares of 15. Okay, so that's what 135, square root of 135, simplified down into. I can't simplify square root of 15 because 4 won't go into it, 9 won't go into it, and 16's above it. So I'm just checking one of those factors, right, of perfect squares to see if one exists. So that's going to give me a 3, and I'm going to say square root of 15. Now, I have a 2 here. 2 goes into 3 at least one time. I can make one group in the 2 come out, and I'll leave 1, right? And then that's a 1, so I don't have a grouping at all on the x's, I mean the y's. So that is my answer. And I can't simplify in between on this out here. Okay, so that is all of that problem and everything that needs to be considered. So this ends section 1-3, radicals and rational exponents, part 2's video.